Your particular requirements for a flight yoke and consequently how you go about evaluating its performance are going to depend really on what kind of flying you do. So if you're flying bush planes off gravel bars, or pushing your Cessna 172 around the circuit, or if you're flying Airbuses into international airports, flying aerobatics, in one sense they're very different missions. But that said, there's a commonality in all of those. We do need to have basically the same control of the aircraft in all of those situations. If we go back to the general flight test, in fact the instrument rating flight test is a good baseline. And assuming you're hand flying in IFR, you need to be flying standard rate turns and maintaining your altitude within, I think it's 50 feet, and your airspeed within 5 knots. So those are, basic requirements that a yoke should be able to support. And we're all quite familiar with the lexicon of evaluation of a flight yoke, so with stickiness, binding, dead zones, detents. So those are the things we have in mind when we're looking at a yoke, and you'll have seen me comment on these things when looking at the Alpha LITE yoke. And as you will have seen in my main review video, there were certain aspects of that yoke that were a little bit disappointing. One of the things I mentioned in that review was the notching in the pitch action towards the centre, and I did casually suggest that it would be worth measuring that systematically to investigate it a little bit more closely. So I actually went ahead and did that and we're going to look at the results of that in this video. And what became clear, really just to confirm my subjective sense of how the yoke performs, but the problem isn't really with the people will complain about the tension of the pitch action, or the heaviness if you like. The problem isn't really that heaviness at all, it's the linearity or the lack of linearity, as we'll see. So let's have a look at those numbers and see what we can see. So let's just look at the measurements we took from the yoke. This is showing a representative curve. What we got here is we're pulling the yoke from the neutral position to the fully rearward position. We've got a little kink at the top here, that's probably me hitting the backstop. On the vertical axis we've got the force that we need to apply, and then in the horizontal axis we've got the displacement. I've not shown figures on here just to avoid too much clutter, but basically at the bottom left we've got 0 displacement, 0 force. Fully to the right on the x-axis we've got about 40 millimeters deflection, and at the top of the y-axis we've got pretty much 4 kilograms. Now the curve's not super smooth. The reason for that is the device I was using to measure the forces could only measure in 100 gram increments, and so we only get about 20 measurements for that neutral to fully rear or fully forward deflection. So this is a measurement taken with pulling the yoke from the neutral position all the way back with 2 hands. So in one sense it's the most conservative way to operate the yoke in terms of the mechanics. And we have 2 independent measurements. So here's the second one. And although, as I say, they're a little bit wobbly, we can see that's pretty much the same curve with a noticeable step in the curve. Here's the same sets of measurements taken with a one-handed pull. So same deal, neutral position to all the way back. And again, although the detail is a little bit wonky, you can see there's pretty much the same signature curve. And if I show you a second set of measurements, again wonkiness aside, we've got that obvious congruence in the overall shape. Now what I should say is one of the reasons I haven't put numbers on the axes is I've moved these curves around till they roughly coincide, and that's because there's a significant, pretty large zone in the centre of this yoke where essentially the springs are not doing the bungee springs are not doing anything at all. So you can move the yoke backwards a couple of millimeters and let it go, or forwards a couple of millimeters and let it go, and it will stay where you put it. So in essence what we're seeing is the starting point in each of I did 6 sets of measurements in all. The starting position in each case isn't necessarily going to be exactly the same, so just to bear that in mind. I don't want to read too much into the fact that the measurements seem more wobbly in the single-handed pull than in the double-handed pull, although it is noticeable in practice that there is more resistance, and so probably more variability in the smoothness really of that movement. Because the other factor is I'm having to pull twice as hard since I'm only using one hand, so we've got to factor that in as well. And the third set of measurements I took was pushing the yoke. It was only possible to measure this for a one-handed push, but again we see that same signature, and again just to show a second independent set of measurements, and we get that same characteristic curve. And so the other thing I can do is show all of those things at the same time. So here we've got all 6 measurements displayed at once, and I think you'll agree that there's a definite correlation there. So what we're seeing essentially is two independent linear ranges of movement. Now linear in the sense that the displacement per unit force is essentially a straight line. So I guess the gradient of that line in each case tells us something about how difficult it is to move the yoke. Now the first thing you'll notice is that for that first short movement, the amount of force we need to exert to move it for a given displacement is greater than once we get past this bend. Now within each of these ranges we don't really experience any noticeable difficulty controlling the elevators. It's this switchover that causes the problem. And if we just put some annotations on here to show us where that gradient suddenly flips, the numbers. So basically from neutral to a displacement of about 6 or 7 millimeters, 6.5 on average, we get this fairly linear displacement. So that's in total we can rock the yoke around the central position throughout about a 13 millimeter range, 1.5 centimeters, let's call it. And that's something that corresponds fairly well to what I was talking about in the test flying videos. I talked about a parking zone in the center. The other interesting thing right off the bat is if we put in another number, that maximum force as required to go all the way to the backstop or the front stop if you're pushing the yoke, again as I said earlier, is about 4 kilos. So that switchover comes about halfway through the range of force that we need to apply. Now that's kind of interesting. I'm not really sure what to make of that, other than this is not about the bungees. It doesn't seem to be a characteristic of the springs themselves. I'm saying springs, the bungees are a kind of spring. So this is maybe more a feature of some mechanical detail of how the carriage that goes back and forwards inside the yoke is connected to the springs. So I think the most significant thing that we're seeing here is this step, this abrupt change in the gradient of the input force is what's causing us a problem. And particularly because that gradient goes from higher to lower. As we pull through this intersection, the force required for a given displacement of the yoke suddenly reduces. In other words, it becomes easier to pull. And that really, I think, is a good explanation of why we get that over control when we're pulling the yoke back through that intersection. And by analogy, if we're pushing the yoke forward through the equivalent intersection, don't forget that two of these measurements are for the push. So we're seeing exactly the same thing. Technically this should be rotated and be down here. In fact, here's a picture of it. So this is the pull range, this is the central position, and this is the push range, or vice versa. But it's that over control tendency that I think is why we get this porpoising basically in the flare. And another thing that's really significant is that over control point comes a very short distance away from the centre. So in the rearward direction, 6.5 millimeters, which is about 15% of the total range of travel. But it just so happens that 15% displacement is pretty much right in the middle of where we need the elevator control the most, generally during the flare. You know, the reality is when you're just pootling along, you'll generally be trimmed and the yoke will be essentially operating around the centre with very small adjustments required, which means we stay within this parking zone. And it's only situations where you need to go in and out of that parking zone where this becomes a problem. And unfortunately, the most obvious situation where you are definitely going to do that is on the approach and touchdown. This is why this yoke is a bit tragic. You know, we shouldn't be seeing this step at all. This linearity is good, so that's probably showing that the bungee springs have a linear action. And as I say, this difference, this gradient difference, is a consequence of some lever effect in the way that the bungees are attached to the moving parts of the yoke. But ideally we'd be seeing a 0 to max linear displacement in the push and pull direction, and the fact that we've got a 4 kilo force wouldn't be any big deal. So there it is, that's the Honeycomb Alpha LITE version. And to get to the point, I've sent mine back basically. I hadn't intended to do that. I bought this yoke in good faith, wanted to test it out. I imagined I would keep it around, maybe sell it on eBay ultimately, but at the end of the day I don't think it performs adequately at all, and to the point where I had the idea that if I sold this to someone on eBay they might try and send it back to me as not fit for purpose. So it's gone back to the Honeycomb Snakebite store on Amazon, and hopefully I'll get a refund in due course. At the end of the day, this yoke doesn't do what you need it to do. That notching of the pitch, it's effectively a detent. It's not a detent, but it kind of is a descent. Centimetre and a half wide. It's right in the place where you want the finest control over the aircraft. So it's going to mess up anything that requires actual piloting skills, if you like. Whether it's your bush plane landings, your simple circuits, your certainly IFR hand flying, it's just not up to the job. It would be interesting to know why. There's probably some mechanical reason for this. I don't think it's in a simple sense down to, I had hypothesised that there was potentially cheaper bearings in this yoke. I don't think it's really down to that. But that step in the spring action, particularly going from heavier in the centre to lighter when you get off the step, is intriguing. And I was tempted to open up the box and see if I could make sense of that mechanically, but I didn't really want to do that because I don't think I would be able to send the yoke back after opening up the box. So there it is, the Alpha Flight yoke from Honeycomb Aeronautical Lite version. I'm probably better off sticking with the original Honeycomb Alpha, going the extra 80 quid, 100 quid, wherever it is, maybe even the XPC.